Very good evening to one and all present here. So in this present module, we are going to see about the basic law of thermodynamics. In the previous lecture, we saw the basic introduction to thermodynamics. What are the different properties of thermodynamics? And what do you mean by a system surrounding boundary? Some of the basic the principles we saw in the previous video lecture series. Now, today, we are going to see about the four basic laws of thermodynamics. So, this is going to be the objective of today's the lecture series, goal of thermodynamic law, or we can say the basic purpose of learning thermodynamic law. So the main objective of thermodynamic law is to understand the various scientific the principle which can be defined within the various the derivative of physical quantity, say temperature, energy, entropy. These are the physical derivatives which can be quantified by describing each the thermodynamic law principle. So which can characterize the system, the thermodynamic system subjected to an equilibrium state. So for the purpose only, all the four laws are being stated. Now we will see each and every the basic law of thermodynamics one after the other in a correct sequence. First, we will go with the zeroth law of thermodynamics. So what do you mean by the zeroth law of thermodynamics? How zeroth law of thermodynamics is closely associated to thermal equilibrium concept. Let us take the diagrammatic illustration. So take three body A, B and C which are kept close contact with each other, A, B and C, all the three bodies. So here we have to prove that the thermal body A equal to B, similarly A equal to C, and finally B equal to C. So this is the way in which we want to prove all the three bodies are in thermally contact with each other. To understand the principle, just I can give another example by diagrammatic illustrative method. You take two thermal system with the various temperature. One is available at 10 degrees Celsius, the other one which is available at 20 degrees Celsius. Now the thermal body A and B are going to kept in contact with each other under the room temperature. Okay, two bodies are kept within the room temperature limit. So what will happen? Slowly the heat is being transferred, exchanged from the higher temperature to lower temperature. Okay, see the changes happens in the later part. See now system A and system B, two thermal bodies maintaining the same equal level of temperature, each showing 15 degrees Celsius. So how that thermal equilibrium contact is maintained? Say earlier B shows 20 degrees Celsius. When some amount of heat is lost from B to A, okay, so from 20 it has been reached to 15 degrees Celsius. That is within the control of room temperature. The system B maintain its the thermal equilibrium. Same system A, earlier it was 10 degrees Celsius, very low temperature. Now, due to the gain of heat by transferring the heat from B to A, so it maintains the same temperature limit as similar to body B, system B. Now finally, both system A and B are thermally equal with respect to the temperature. This is how they proved the thermal equilibrium concept by zeroth law. Who has introduced this zeroth law principle? So James Clerk Maxwell. So he has defined the statement, the zeroth law of thermodynamics in 1872. The next one, first law of thermodynamics. So the first law of thermodynamics purely based on law of conservation of energy. What is law of conservation of energy? You take any thermodynamic system, the energy can be utilized for converting into another various form. So it can be converted into, say, for example, heat energy into a work, useful work. But we cannot completely destroy the energy. That is not possible. As per the first law of thermodynamics, energy can neither be created nor be destroyed. So we can use it into various workable form. So change in internal energy, delta U, that is the main thing which is applicable for describing the first law of thermodynamics. So the change in internal energy is nothing but U2 minus U1, where U2 is the final internal energy of the system and U1 is the initial internal energy of the system. So it can be rewritten as delta U. So it is an additive of two components. You take heat exchange from the system to surrounding, then the work done by the system. So these are the two additive, the components that has been added to find the change in internal energy equation. These are the two path function, Q and W are the two path function which describes the first law of thermodynamics. So in addition to that, the first law of thermodynamics, the various sign convention things are described by solving the problem related to first law of thermodynamics. Say, if your process, say, work is done by the system, then we call it as a negative work done. The sign of work will be negative. On the other case, you say work done on the system, then it is a positive work done. Suppose if the heat is released from the system to surrounding, then it is said to be negative sign of heat. Here there is no possibility of work done. There is no sign of work done. So these are the various the rule of thumb we have to follow when we are when we are solving the numerical, the quantitative model under the first law of thermodynamics. The next one, second law of thermodynamics. So there are two, the law which describes the second law of thermodynamics. One is a Clausius statement, the other one, the Kelvin Planck statement. First, let us go with the Clausius statement. So the Clausius statements that purely describes the heat can be transferred from the high temperature body to low temperature body without the help of external source. But the Kelvin Planck statement proposes that energy cannot be transferred easily from the lower temperature to higher temperature. With the help of external source, we cannot able to do the energy transfer from lower temperature body to higher temperature body. So this is a diagrammatic view of expression for second law of thermodynamics. Finally, we are in third law of thermodynamics. The third law of thermodynamics describes about the concept of absolute zero temperature of a perfect crystal. Absolute zero temperature of a perfect crystal, which is maintained at 0 Kelvin. In that case, the entropy of the gas molecule will be maintained at zero. It is not greater than zero. So let us see the physical illustration, the graphical illustration. See, if the temperature is greater than 0 Kelvin, the movement of the gas molecule kept inside the tight sealed container, that will be quick, very fast, and randomness. The movement, the path movement will be randomness in nature. So entropy will be greater than zero if it is not maintained equal to 0 Kelvin. So if you reduce the kinetic energy of the gas molecule uh, slowly below the room temperature, that is absolute temperature 0 Kelvin, all the gas molecules will be equally settled down within a perfect, well-definite order. In such case, the entropy of the gas molecule will be zero. So this is how the property of entropy, how it becomes zero at absolute zero temperature. That can be stated using zeroth law of thermodynamics. Sorry, third law of thermodynamics. So what are the outcome of the basic law of thermodynamics? So whatever we saw, zeroth law, first law, second law, and third law. So these are the things which we can apply in any real case day-to-day life application, that is applicable to any real case day-to-day application, which has been listed here in the outcome slide. So with this, I thank each and every one of you for your kind support. So in the next meeting, we will see the remaining component of thermodynamics with much more practical examples. So thank you one and all present here.